start. The topic today is security. Why will we speak of security? Well, because as energy engineers, we will be perhaps working on energy systems, but certainly also on software and computer systems. And it's important that you're able to, for example, do things such as secure socket programming. So we will see today what are the things that are below and other things. Because cybersecurity is a very important part of the threats on energy systems, the electrical grid in particular. There are many known cases. I mean, the first publicly large-scale attack that was done using cyber attack on the control system of a big diesel generator is pointed here, and that caused the generator to physically fail. I mean, if you play with the control, the goal of the control of a diesel generator or of a battery, the energy management system, the battery management system, has responsibility in the safety of the device. So if you find a way to fiddle the system and change what the control is doing, then it might bring the system into having physical parameters that bring it out of operational range and might even destroy the asset. In the context of the Ukraine war that started in 2014, there were attacks against the electrical infrastructure of Ukraine. Now, the attacks are very brutal and kinetic. They are done with missiles. But when the war started in 2014, it was done on cyber ways, essentially by trying to gain control of some of the control systems of the Ukrainian grid. And how was that done? Well, it was done by stealing passwords of some operators. Some of you have received a mail. I guess you all have received a mail from pretending to be from me last week, right? Asking you to type in your credentials on a web page. This is asking the question, how do I know whether it's okay to type in my password on this page, right? So that's the page I expect to see. This is when you log into something like Moodle, for example. Here's the mail you have received, right? It pretended to be from me, but it was from an address on Gmail, a strange address, that was saying you need to sign a user agreement and privacy policy for an electricity company. That does not exist, by the way. It was forged, this electricity company. And this is what you had to read and sign, put your username and password. And fortunately, of course, that was all done by me, but it could have been done by anybody because this is an email coming from Gmail. This is a web page that's on GitHub. Any of you can have a free account on GitHub and write your mail pages there. And then if you click on it, if I had done the thing with a malicious intention, I would have obtained all the passwords of the 20 or so people who clicked on it. And of course, if you look at the source code of this web page, the HTML clear text of the web page, it does not really send anything out of the page. So that when you click here, you come to a page on Google Forms that has not received this. But you were at 1 millimeter. If I had done the form differently here and there, I would have received your email addresses and your passwords. Right? So then I could send an email saying, I am locked outside the building. Can you please do this for me or whatever? And then, of course, you can imagine easily all the kinds of things that could happen. So how can we know whether this is a valid page to type in my mail, my credentials into? Right? This is very simple. It doesn't require a lot of science or introduction to cryptography like we will be doing today. And because it's simple, it's the most widespread attack. This is how, for example, the Ukrainian grid attack that I mentioned was successful. Sometimes it's more brutal than that. I mean, sometimes in the context of industrial networks, of Smartgrid, for example, sometimes you have your own password, but sometimes you also have the password of a device, of a PMU, or the PDC, or the SCADA. And sometimes there are multiple operators who have to play with that. And so companies that are poorly organized, they give a password per device and not per person. And since there are multiple people who may use the device, sometimes you put it on a post-it on top of the machine with a password. If you're here, log in. Of course, this is stupid, but this is how, for example, an attack was successful on the French radio news, France Info, the Radio France International, was hacked simply because they had the passwords on stickers, and people who visited the place had the password. So password protection is, of course, essential thing that hasn't to do with a lot of science, but is very important. So if you work in an energy company or a smart grid or an operator, and if you see things like this device has a password which is put on a sticker somewhere, then you should complain somewhere to the cybersecurity specialist. Hopefully there is one, but if such things happen, probably there is none. So some rules are, for example, that when you log into a system, it should be with your own account. Me, Jean-Yves Le Boudec, that I should type into this machine with my account by going to sites like, not this one, hopefully, but like this one here. So that will make it possible. If my account is compromised because I was not very careful and I've lost my password, that can always happen. We're all human beings, so we're not perfect. We don't do catastrophes usually, most of us, but we are also not perfect. So our passwords will get stolen once in a while. It's not, we cannot guarantee that this will not happen. Then it's important to be able to repudiate a password and an account if I know that your password has been compromised because you've given it to some attack of this kind. Then we can revoke it, and at least the machine here is not compromised. So this is what we discussed here. Beyond passwords, companies like EPFL or sites like EPFL don't use a lot of two-factor authentication. The state of the art today is that a password is not enough, but you need other mechanisms like two-factor authentication that we will discuss in a few more minutes here. So security is, of course, going beyond simply losing the password, because the password is used as a mechanism to reveal or gain access to authentication and encryption. So authentication and encryption are the standard systems that are used to protect against all the attacks that are listed here. Confidentiality has to do with the fact that when A sends a message to B, well, on the internet or on your MAC layer, Wi-Fi, Ethernet, etc., we have seen that in many cases it's possible to read the messages or to using wrong ARP reply, address resolution protocol replies, we can get the messages. So if an attacker manages to do ARP attacks, they will receive all the messages from A. Now, to remain hidden, they will, of course, continue sending them back to B, but of course, there will be a breach of confidentiality. E will be able to see everything, and perhaps you don't want this to happen. Why is it important to have confidentiality? Well, a lot of information is truly confidential. That's the business marketing information. You're preparing to do a reply to a bid. You're going to offer a service at a certain price. If your competitors have access to that, of course, they will give the same price as you, minus 1%, and then you will lose the bid. So it's important for business information to keep it secret. But beyond this, it's important to keep everything as secret as possible if you have a critical infrastructure, because attackers will use the knowledge of how your system works to make maximal damage to it. So by making the operation of your grid or of your energy system hard to read, then you make also the job of the attacker much more difficult. So confidentiality is very often something that people would like to have. It's also important to have what is called integrity. Integrity is the fact that when a message is sent, for example, a PMU reading is sent to a control center or to the PDC, then this message is not modified. Because if you modify it, you can modify the value of the phase angle, for example, then you will modify the information that the control center will receive. For example, the phase angle, as we will see in a few more weeks, is at first order an indication of the power flow. The difference in phase angles between two nodes on a grid is roughly proportional to the power flow of the line. Now, if the goal of the control system is to monitor the currents on the line to avoid that there is problems, congestions of the lines, then you can fool the system. You might say to the system, well, the line has a current which is only 50% of what it really is, which means that the control system will induce that the power flows are much less than they used to be, and might decide to divert, for example, more power into this line, which will cause the line to trip. Of course, there will be physical mechanisms that will break a line if there's too much current in it, but the goal of the control system is to prevent this from happening. So you can attack a grid by simply forging the messages. And you can imagine all kinds of messages can be forged. For example, if I instruct my bank to pay a bill to someone, and then you can change the destination, the IBAN destination account, of course, the money will go not to whom I'm paying to, but to someone else. And then I have lost the money, and I will have problems. And it's a way of stealing money. Sometimes it's also interesting to do what is called non-repudiation, like A sends a message to B, and then A pretends, no, I've never sent that to you. I said to you, sell all the Credit Suisse shares 5 weeks ago, and you didn't do it, so now I sue you because you didn't do it. But in fact, I can pretend I did not send this message in order to attack somebody. So that's another type of attack that we will see, techniques that can achieve protection against. An adversary, like the bad guy here, can be passive. That's the case of somebody who's just listening to gain intelligence into what you're doing. But intelligence is usually the first step in an attack. Or active, that's the case that a message is being transformed. And we will see that it's important to be secure against those type of attacks. To bring security, there is a number of mechanisms that are essentially variants of encryption. And there are two big families of encryption, symmetric and asymmetric. So we'll say a few words about it. Of course, encryption is itself an art and a science. So there are entire labs at EPFL who work on such topics, like Serge Baudnet's lab, for example. But what we will do is give a mental model of how it works to be able to use it well. So the first system we're looking at is symmetric cryptography. So with symmetric cryptography, we have a message that we want to encrypt. It's called a plain text in the language of cryptography. And we have a key. And the key is secret, should be kept secret. And the key is the same at the source and at the destination. So when you have a message to send, you apply an operation that requires the message, the plain text, which you would like to keep secret. That's the goal of this mechanism here. And you somehow use as second input the key that produces a text, which is called the cipher text, which in practice looks like a random sequence of bits. So it's a random sequence of hexadecimal digits. And the hope is that if the system is well done, any attacker that sees that essentially sees something that is ununderstandable. Now, when you receive such a message, this type of system requires that you know also the key here, and you apply a reverse operation called decryption using the same key, the received ciphertext, and hopefully that will produce exactly the plain text. And the assumption is that the attacker does not know the secret key, therefore is not able to perform the decryption here. Of course, it works as long as the key is secret, but it works also as long as the system is strong enough. Here is one of the very first published crypto systems, published 2,000 years ago, Caesar Cipher. The key here was a number between 1 and 26. It's a very poor system, but at that time, there was no paper, at least not in Europe. And so it was not easy to write things. Writing was a very clumsy thing you could do on sand or on stone. And very few people could read and write anyhow. So it was sufficient to have a very primitive scheme. This primitive scheme was, the key is a secret number, which is simply a letter, which is interpreted as a shift. And we do a circular shift in the order of the alphabet. So here I'm between 1 and 26. I think the Latin alphabet doesn't have that many letters, but for the purpose of this illustration, let's do this. For example, if the shift is 3, then this simple Caesar cipher will replace every letter A by D, B by E, and Z by C, etc. For example, AVE will become DYH. And Julius Caesar and his officers used this to send messages that were, if you read Asterix, that was carved in stone and sent over people riding horses to some places. Here is an example sent by Julius Caesar. Here is the text that was sent. So if Asterix would catch the messenger, they could read this text. Do you think they would be able to decipher it? Or since we are in the 21st century and we are smarter, at least we have been trained to use smarter tools, are we able to decipher this one? So you should see on this number of speak up, you should see the poll open. I close the poll in a few seconds. Closing. And then everybody says C, which is true. So congratulations, you are able to defeat the cryptography of the Romans. Here, we can do a brute force attack. There are 26 keys. So with today's computers, or even at that time, if you had enough paper resources, you try you shift the 26 attacks, and you look whether you have something that makes sense. And in this case, there's only one sentence, which after inserting spaces looks like a Latin sentence. So this is the only one. You could also have seen that since this is a cipher that's very primitive, that always replaces the same symbol by the same symbol, you could analyze that this, for example, could not be the same as that, because here we see that the Y, the second and the fourth should be the same, which is true here, but is not true, for example, for this. So you can exclude some of the potential sentences by simply gaining information from the ciphertext. Why am I speaking of that? Why are we playing with this cipher, which of course is by no way usable today, even though it was used 2,000 years ago? Well, because this illustrates that the belief that the attacker does not have the secret key might not be sufficient to protect you. There might be information that is leaked from weakness of the crypto system, which is the case here. We know it cannot be this, it cannot be that, it cannot be this. So you don't know exactly which one, even if you don't do a brute force attack. But if you're suspecting, is Caesar saying withdraw from this city or bring more people? So you have a small number of options, and you try all of them and see whether they correspond to feasible encryptions. So take-home message, a cryptographic system might be weak and might reveal information even to an attacker who doesn't have the key. And that's the problem that was historically present in many systems. So Caesar cipher is not strong enough. One of the reasons is easy to understand here. There are first, the structure is not shuffling the information enough, in the sense every character is always translated to the same. So it's very easy to do analysis of the text. But also the key is too small. I can do a brute force attack by simply trying all the possible keys. That's why, and that is always possible. whatever the scheme, you can always do a brute force attack. So the key must be large enough. For example, with the system that is used, the mostly used system today, which is called AES, Advanced Encryption Standard, it uses a key size of at least 128 bits, which gives 10 to the power 38 possible keys, which then makes it hard to do a brute force attack. Perhaps it's possible if you work, if you use a huge amounts of resources, all the resources of a country on a single message, but otherwise it's going to be very hard. So let's say a few words about this system, AES. That's the one we use when we do e-banking, for example, and when in the Smartgrid, when we encrypt messages between a PMU and a PDC. It is a block system, block cipher. Cipher means encryption system. It's a block cipher in the sense that it takes plain text that must be chopped first in blocks of 128 bits. And then it applies some encryption mechanism and produces a ciphertext, which is also a block of 128 bits here. What it does really is a set of permutations. For example, a mental model of what AES is doing is you write on the y-axis on the left all the possible sequences of 128 bits. It's as many as IPv6 addresses, and that's a huge number. We're not able to write it, of course. There's not enough space in any computer to write them all. But as a mental model, imagine you do this, and what it does is it maps each of those unique permutations to another permutation in a way that's one-to-one. So for any sequence here, for example, the sequence 001, the loopback address, if you want, is mapped to something which is an arbitrary sequence of zeros and ones, and there's only one that is mapped here. This is required because we want to be able to decrypt. If I send you an encrypted message and I have the key, I should be able to decrypt. So it's a one-to-one mapping, bijection of the set of all possible sequences here. So it must be invertible here, and different keys give different permutations, of course. So the goal of the key is to define a permutation here. With a certain key, it does this. With another key, it does that. How does it work? Well, we'll not see that in detail, but here is a high-level glimpse of what it does. It does a bit, it uses a principle, if you want to play card, you have to shuffle them. So you use several tricks. First, you break the heap of cards into two, then you shuffle them, then you break it again, then you shuffle them again. That's essentially what it's doing. So it's shuffling the input here. If you take an input, which is a block of 128-bit, the key, which is also a 128-bit, then you XOR the input and the key. That gives you a first amount of shuffling. And then you do a number of operations that consist in writing this 128-bit in a matrix, and then not randomly, but according to an order that's derived from the keys that we have here. You shift the row and you mix the column, and you also do some other operations here, and you do that 10 times here. And you hope that by doing that, you've shuffled the thing enough so that it's impossible to revert this. It is believed that AES does not provide information about the plain text, unlike Caesar cipher. We've seen that Caesar cipher, even if I don't know the key, I can have information about the plain text without knowing the key by just counting letters and seeing whether the same letter is repeated and so on. Here it is, has been extensively researched, and it's believed that this is not the case here. I say it's believed because this is not mathematically proven. There is no mathematical proof that it is impossible, which is an apparent paradox. I mean, we would hope that cryptography is more scientific and we can mathematically prove that it is impossible to gain any information, but this is not the case. All the proofs are always done within a given model. If we assume this and this about what the attacker can do, then we can prove it doesn't work, but we don't know whether an attacker will have new means to provide a new attack, which means that any cryptographic system that is believed to be secure today is secure as long as there is no indication that it is not. And a consequence of this is we must be able to quickly change the system that we have. For example, before AES, there was something called DES, Data Encryption Standard, has been used for many, many years, and has been shown to be broken. That somebody has published an attack, a very complicated attack that allows to, in some cases, gain some information about some of the text, and then this was abandoned. This standard was abandoned and replaced by AES. This is how things are with cryptography. So don't believe that because you have your cryptographic system now, you can hard code it in your hardware and be, say, secure forever. No, you're secure as long as your cybersecurity specialist in the company, or if it's you, that by going to the NIST website, who publishes what is the state of security of the known systems. As long as it's not published that it's unsecure, that's the only guarantee you have about security. So it's a bit less reassuring that we would like, but this is how things are. So AES is believed today to be immune to known plain text attack. And also the reason AES is very popular is that it's very fast. So those operations on shifting bytes and columns and etc. and doing XOR, those are operations that a computer can do extremely fast. So less than a fraction of a millisecond, order of microsecond, to encrypt a sequence of blocks of 128 bits. That's why it is used everywhere. So it is immune to what is called known plain text, known plain text attacks. That means if we have a text that we want to encrypt and it is encrypted, then we're not able to find it like we were able to do with Caesar Cipher. However, there is another problem that may occur, which is called the chosen plain text attack, which typically occurs when we have measurements, for example, or computer systems, where we tend to send the same message again and again. And because AES uses blocks, if the same block is seen multiple times, then if I know, I will gain information. For example, if the same protocol header, the IP header, for example, we've seen that an IP header is 40 bytes plus TCP that will add another 20 bytes. So there are 60 bytes. So that makes a big part of a block. And after that, you may have information about the application layer, which are always the same. So you can see the same word again and again. And so formally, if you have a number of blocks M1, M2, Mn that are encrypted, and you've seen the pairs MI, CI a number of times, then that may give you some information, either because you have forced the attacker, the crypto system, to encrypt something by submitting a value, if you have this capability. Then if you've sent the message M3 to the encryption and you've seen the ciphertext C3, the next time you see C3, sent perhaps by some other device than you, then you know that what was sent was M3. Right? That's if you can have access to forcing the cyber system, the cipher, to be applied to your message. But sometimes also it can be that you see something that you see the same thing repeated many, many times, a bit like in Caesar Cipher. If we see the same letter many times, we think, well, what is the most popular letter in French, for example? It's E. So this letter must be E. So I know already where all the E's are. So I can gain some information about the text that will help me perhaps not have exactly, that's not me, but it's the same music. So that might help you gain some information here. So AES alone is not used as is because of this fragility here. And this is thwarted by what is called using a nonce. So a nonce is a combination we add to the key by adding, for every block that we encrypt, we combine it with another message, another number, which can be public, but the goal is simply to make sure that all the blocks that are encrypted are different. Even if I'm sending the same word, or the same block of 128-bit multiple times, it will be combined with a nonce that will make it look different. For example, there are two variants of AES, AES-CBC and CTR. The simplest to see is CBC. The CBC stands for chaining. When I have a block to encrypt, I encrypt it with a key, but so So I use the key here, and then I use an initialization vector, which is a number that can be public, doesn't have to be secret, which is, for example, a random number, which I XOR with my thing here. It has to be public because the destination will need to know it. Then the next block will be encrypted after XORing with the encryption of the previous block. So if I have a message that fits into 3 blocks, like here, I encrypt the first M1 with this number here. I obtain C1 here. Now, M2 will be XORed with C1, and C2 is the encryption of M2 XOR C1, and so on. So if M3, for example, is the same as M1, then C3 will not be the same as C1. In order to be able to do the reverse thing, I need to start from the first. I need to decrypt C1 correctly. Only after decrypting C1 and obtaining M1, I am able to decrypt C2 and obtain M2, etc. So this will make sure that all the different blocks, even if they are seen again and again, will give completely different cyber texts here. So there is this way of doing, which is very often used. There are other ways that simply are even more primitive, but for some reason seem to work the same way. You simply start with an arbitrary counter, which can be public, and you increment it for every block that you do. For example, you choose some number here. A number on 128-bit can be a big number, a random number between 0 and 2 to the power 128 minus 1. You add this to the message you want to encrypt. You encrypt this number with AES, and you XOR it with the message that you wanted to encrypt. That gives you C1, and you do that for all the systems here. So there are 2 variants. So take-home message here. AES needs to be complemented with something like a nonce to obtain CBC AES, for example, which is a symmetric encryption scheme with key sizes that are large enough, at least 128 bits, is very fast, and provides confidentiality. That means that it is believed that an adversary cannot gain any information on the clear text from reading the ciphertext here. There are many other things at AES. This one is the most popular. That's why we have a glimpse of it. I mentioned DES, that was similar to AES, but was broken one day. So an encryption scheme is secure only as long as it's not proven insecure, which means that the secure socket layer, for example, that we will see in a few more minutes, must be able to change not on the fly, but must be, whenever you do the next update of your software system, must be able to change the encryption method and has to be updated regularly. This is one of the motivations for keeping a system up to date, which is also one of the major pains of software systems. You could say, my system is secure because it's completely closed and nobody knows how it works, and I'm using software that was done 20 years ago. As, for example, the railway system of the French railway stations had been using that, so they used Windows 2 or even a few years ago, and it was completely closed. At some point it was broken and it could be attacked. So that's probably not an option. So the other option is to always have your system up to date, at least do all the security updates. One of the reasons would be this: when you move from DES to AES, well, you have to make sure your secure socket layer does not use DES anymore, because of course the bad guys know, probably even before us, that those weaknesses exist here. Voila, little quiz. I'm closing the poll in a few seconds. Closing. And of course, the answer is A and B are both correct. It's a block cipher that encrypts blocks of 128 bits, and it's invertible for who knows the key. Another small question. Closing. Majority says G. Is probably not correct. So a nonce should never be used more than once in combination with the same key. That's the definition of a nonce. So that's A is true. A nonce need not be secret. Well, it's true. In fact, it's worse than that. A nonce must be known to the receiver. So because otherwise you cannot decrypt the system. A nonce must be random, not necessarily. We've seen that the counter-based scheme can use perhaps a random for the first one, but it will be published then. And then all the other ones are deterministically derived from it. So all possible systems exist. Well, that was our first element, which is an encryption system that provides confidentiality. Now, we also want message authentication. That means we should prevent an attacker, like this bad guy here, from forging a message, changing the values of a message in order to prevent bad things that could happen on our system here. For this, one technique is called the MAC, Message Authentication Code. Same acronym as the MAC layer, but it's not the same at all. So all three letters acronym of multiple meanings. That's an example of this. Message authentication code is a little block here that we add to a message. How is it done? Well, if we use symmetric system, like for cryptography, there is a secret key that must be known to the two communicating ends. When I have a message to send, I compute with the MAC what is called a tag that I add to the message here. And then when this is received, I will also know the key. I know also the message that is done. So I apply the computation or the reverse, the same computation, essentially. I recompute the tag here, and I look whether the tag that I have computed is equal to the tag that I have received. If so, I believe that the message is authentic because this relies on the security property that the assumption is that an attacker who sees this message and the tag and would like to forge the message would be unable to compute a tag that is valid for the forged message unless the attacker knows the secret key here. That's the unforgeability assumption here. Here is a simple tag system, a MAC system that has been invented by our friend Homer. Homer has taken a course in communication systems and has learned about things like error detection codes. So here is, for example, the kind of things that we do in communication theory or in coding theory. We use number theory to produce things like this here. So this way of computing the tag is using modulo arithmetic. I pick a prime number. In reality, it would be a huge number, but here I'm picking 257. And the tag is computed by doing this affine transformation. I first transform the message into blocks that I interpret as integers modulo p. And for example, if I have the message hello, I will write the hexadecimal ASCII representation of all the letters. And each of those blocks here are interpreted, a block of two numbers here is interpreted as a number. And I apply this computation. I multiply the message, which is now a number modulo 257, by A, a fixed number, 58 here. I add B, and I do modulo P. Because the modulo is a sort of shuffling everything that gives us a way of doing the tag. For example, if I have this message, I transform it into numbers. I apply this computation, I obtain 35, which is a tag. It is used for detection, because we know that if we do this, if you send you this message and that, if there is a bit error somewhere that has transformed one or a number up to 8 bits, here at 8 consecutive bits, in fact, then the tag will be wrong, or the tag and the message will not correspond anymore. So that is what is called a detection code, which is used everywhere in Ethernet, in all the systems we've seen in the past weeks. We use such systems to verify that the message has not been affected by errors here. If we work a bit more, we can even use this message to recover with high probability some of the errors. So the idea is to use the same trick for a Mac here. For example, if I'm sending to my bank a message saying transfer that amount of money to this account here, then the attacker finds a way to get my message and transform the destination IBAN. But the problem is now the tag that I had computed by number crunching all this and applying the method I've given before. It gives F7. Here, if I transform the message, it should be 7-4. But since the attacker doesn't know that the key is 58 and 180, he's unable to compute this, and therefore, when my banking system receives this message, it knows this message is corrupt and will discard it, and perhaps flag that there is an attack. Do you think this is a secure Mac? Closing the poll. The majority says C, so you don't trust this thing here, and you are right, because this is a very bad Mac, in fact, because if you see two combinations of messages and tags, if I see M1, T1, M2, T2, so if I'm the attacker and I see two messages, I will simply have to solve this set of linear equations. Now you can say, well, yeah, but this is all modular arithmetic. Well, when you do modular arithmetic with respect to a prime number, everything is like the usual computations we do in MATLAB or linear algebra, the usual way. So we can solve this system of equations by the standard way, and we obtain, for example, this formula here. Now you need to be lucky. You need that M1 and M2 are invertible modulo P. That means they are modulo P. They are not equal. They're not equal here. And by doing this computation, which are very easily, you can do in Python or MATLAB very easily, you will obtain A and B. So that's a very bad Mac, because it means by seeing two messages, I'm able to recover the secret key. Of course, we would like this not to happen. So a secure Mac could not allowed to find the key or even to be able to forge a message. This is called create a collision, where it should not be able to forge a message that has with the correct value of the tag here. A very frequently used tag system, or a MAC, is also reusing our friend AES that we've seen a minute ago, which is called CBC MAC. So it's not CBC AES, but it's the same idea. It's chaining. The way it works is we use the AES encryption system. Remember, AES takes blocks of 128 bits and a key, and then transforms it into a cipher block here. Here, if I have a message and I want to compute its tag, I start with this, which is the length of the message in bits here. I encrypt it using AES. The result of the encryption is XORed with the first block of 128 bits of the message, which is then encrypted, again with the same key, and etc. until the last block. And if the message is not a multiple of 128 bit, I pad it to make, with zeros, for example, to make it a multiple of 128 bits. And at the end, I obtain a tag, which is a single block of 128 bit here. This is the chaining mechanism. And it can be shown that if you have an encryption system that is secure as an encryption system, that in the sense that it's not possible to infer anything about the plain text simply by observing a sequence of plain text here, then it also provides a secure MAC system in the sense that it is not possible to forge a message and a tag that correspond to what we want without knowing the secret key here. So the belief that AES is secure means that this CBC MAC is also unforgeable here. So this is what is used, for example, when we do e-banking or when we use the encryption when we authenticate messages in a smart grid. Now this is 128 bits, so this is, for example, what will be obtained. Now, when I'm transferring a message to the bank here, this is not validating using simply 2 hexadecimal digits like with Homer's system that was not very secure. You will have something like this that's has the same size of an IP address, IPv6 address, but appears like a random sequence of hexadecimal numbers here. And if I change anything here, I need to recompute this, and the belief is that there is no way to, by changing this to be what I want, to find exactly the correct tag here. Now, of course, this provides what is called integrity. If I do only this, I am not hiding the message. In reality, most of the time, we want to do both. We want to have confidentiality and integrity. So this is combined, for example, by many systems, the ones we use on the internet, by this here. So if I have a message, I have one key that is used for encryption, another key that is used for the MAC here, for the computing the tag. And one way to do it, which is the widespread one, is first we encrypt the message with a key. We obtain the ciphertext C. The ciphertext is then validated with the tag here that gives us the tag. So what I will receive is C and T. T is validating the ciphertext, which of course will not help anybody if you don't know what the ciphertext means. So when I receive this, I will use the key K prime to validate that there has been no tampering, no modification by an attacker of the message that I've received. And so then I can only then believe that C is really what has been sent by my correspondent, and then I can start decrypting it here. This is how they are typically combined. Take-home message. MAC uses a secret key known by sender and receiver, produces a tag used for verification of the authenticity of the message. And hopefully it's secure, which means it's not possible to forge a tag unless you know the secret key. And we have seen that the most widespread MAC is in fact derived from a block encryption scheme here. And MAC alone does not provide confidentiality and has to be combined with encryption. Voila, that's our first hour. We do a break.